will talk about the Fourier transformation. Fourier transformation has a wide number of applications in communication engineering, wave propagation, and even in transmission line. I have already given you the definition of the Fourier series, and we know that the Fourier series Fx, which is your periodic function, decompose a function Fx into a finite number of, into a set of, you can say, discrete set of frequencies with the multiplier as a fundamental frequency. But the Fourier transformation provides a continuous resolution of a, you can say, a non-periodic function. So first of all, I will start with the definition of the Fourier integral, and then we will establish some formula for Fourier sine transform, Fourier cosine transform, Fourier transformation of a function, and then I will give the definition of the complex form of the Fourier integral. And finally, we will try to solve some questions related to the Fourier transformation. First of all, let us define Fourier integral. Let capital Fx be a piecewise continuous function in every interval of minus infinity to infinity, and suppose that, and let this Fx is absolutely integrable in this interval, and suppose that this function is integrable, then the Fourier integral of Fx is defined as, and the Fourier integral of Fx is defined as Fx equal to 1 pi 0 to infinity, then minus infinity to infinity, ft cos s t minus x, then dt, and at outside we will have ds, where s is the same parameter as we have seen in Laplace transformation. Okay, this is known as the Fourier integral of a function Fx, that is equal to 1 pi 0 to infinity minus infinity to infinity Fx cos ln st minus x dt ds. Now, with the help of this definition, we will define our Fourier integral, Fourier sine integral, Fourier cosine integral, and even complex form of the Fourier transformation. So, okay, now here you can see that this cos, you know that cos theta is even function. So here we can see that this cos s is even function. Now if this is our even function, then this equation A, say it is 1. Now 1 can be written as, this equation 1 can be written as Fx equal to 1.2 pi minus infinity to infinity, then minus infinity to infinity ft cos s t minus x dt ds. Because this cos theta, because this cos s is even, so this integral will be 2 times. So this 2 and this 2 will be cancelled, and we will get the same result. Okay, now this is your even. So we have this result. Now, similarly, this is because of this result of definite integral cos s, that means cos theta, d theta is, or you can say that cos x ds is same as 2 times 0 to infinity cos sx ds, because this cos is even function. So that is why here we will get to, and by that we will get the original result. Now again, also we know that sine is odd function. If we write sine at here, then as sine is odd, so this will not become 2 times and it will be your 0. So again we can write 1.25 minus infinity to infinity minus infinity to infinity ft sine s t minus x dt into ds equal to 0. We can write this is equal to 0 because your sine theta is odd function. So let us assume this equation number 3. Now for equation number 2 plus I times 3 will give you 2 plus I times 3 will give fx equal to, now everything will be common and here we will have cos theta plus I sin theta. So we will get 1.25 minus infinity to infinity minus infinity to infinity ft, and then in the bracket we will have cos st minus x plus I sin st minus x, and then we will get dt into ds. Now this is your cos theta plus I sin theta, which will be your e to power I theta. So we will get 1.25 minus infinity to infinity minus infinity to infinity ft e to power I st minus x dt ds. Now this result, this equation number 2, say this is equation number 4. Here equation number 4, equation 4 is known as complex form of function. This equation is known as complex integral form, complex Fourier integral, you can say Fourier integral of a function fx, of a function fx. So this equation 4 is your complex form of a Fourier integral. Now it has very good deduction. Now please note down the formula. We can break it in 2 parts. So therefore our fx equal to 1 upon 2 pi minus infinity to infinity minus infinity to infinity ft e to power ist into e to power minus isx dt ds. Now we have some choice. Either we can assume this one as, now this is in terms of t. So after integration of this to t, we will get some function of s. If this bracket, say, let us denote this by small fs. So if small fs equal to minus infinity to infinity ft e to power ist dt. Suppose that this is your small fs. Then our capital fx will be 1.2 pi minus infinity to infinity. Now this bracket is your fs, so we will get fs and then e to power minus isx ds. So with the help of this result, we have got this beautiful formula. Now this fs here fs is known as, this fs is known as Fourier transform of function fx. That is, the Fourier transform of fx is equal to fs, and we have fs equal to minus infinity to infinity ft e to power ist dt. So this is the Fourier transform of a function fx. So it is very easy, and the Fourier transformation of a function fx is equal to this integral, where this fx, capital Fx, is known as, and the Fourier inverse transform is, now here you can see that our Fourier inverse transform will be capital Fx. If you write f, capital F inverse here, then we will get Fx. So the inverse Fourier transform in this case will be your 1 by 2 pi minus infinity to infinity Fs e to the power minus Isx ds. So this is known as Fourier inverse transformation of the function Fx, or you can say of the Fourier transformation Fs. So this is the one set of Fourier transformation and inverse transformation. Now please note that here this was the one way of writing. We can have another set of Fourier transformation and inverse Fourier transformation. Suppose that now this 1 by 2 pi can also be written as 1 upon root 2 pi here and 1 upon root 2 pi here. We can also write this Fx equal to, say, again I am writing this equation again also. Now this, say this is from equation number, I think that was equation number 4. Also we can write Fx equal to, now 1 by 2 pi can be written as 1 by root 2 pi, then integral minus infinity to infinity, then integral 1 by root 2 pi, integral minus infinity to infinity, then we were having our, what was the, in the bracket we were having the function. Now this was your function, and in the bracket we were having e power ft, e power ist dt, and then ds, and 1 e power minus is x into dx. So this was our equation 4. Now if you write this as the Fourier transformation of Fx, now if we write the Fourier transformation of Fx as Fs equal to this term 1 upon root 2 pi minus infinity to infinity ft e to the power ist dt, then our inverse transformation will be so please remember, this was your one set of Fourier transformation and this was your inverse transformation. Now the another set is Fx equal to, now here we will get 1 upon root 2 pi minus infinity to infinity Fs e to the power minus Isx ds. So these are two formulae and you can use any one. We have two set of formulae. This is your one set, say equation number 5a and 5b. This is your Fourier transformation of Fx, and this is the inverse Fourier transformation of function Fx. And again, here we have the inverse Fourier transformation, and its Fourier transformation was, the Fourier transformation of Fx was minus infinity to infinity e to the power ft e to the power ist dt. So this was the Fourier transformation of the function Fx. Now we can say this is your one set of formula. You can use this one. Say this is equation number, say some equation number a, and we can assume, we can say that this is your another set of formula. You can use any formula, either you can use a or you can use b. We have one more formula and it depends on the choice of the author. Now you can replace your s. If we write s, if we replace s by minus s, then we will get minus s here and we will get plus s here. So there is no harm in replacing, in interchanging s and minus s. So we can have two more formulae, one for the Fourier transformation and another for the inverse Fourier transformation. We can also have minus sign here and plus sign here, minus sign here and plus sign here. This is up to your choice. So some author also use Fourier transformation of fx as minus infinity to infinity ft e to the power minus ist dt, and its inverse as fx equal to 1.2 pi minus infinity to infinity fs e to the power isx ds. So this is up to your choice which formula you want to use, but I will use this formula because it is used to operate. So we will use this during our questions. So this will be our Fourier transformation of a function fx, and that will be your inverse Fourier transformation. You can also use this one as the Fourier transformation of a function fx and this one as the inverse Fourier transformation of fx. Please note that in this formula number v, we have the coefficient as 1/2 pi, and here in the Fourier transformation we have no coefficient, but in case of inverse Fourier transformation we have a coefficient 1.2 pi. Note down these two facts. So let us define the Fourier sine and cosine transformation. Fourier sine and cosine transform. The Fourier integral this was the Fourier integral of a function fx 1 pi then 0 to infinity minus infinity to infinity e then ft cos st minus x dt ds. This was our Fourier integral. Now let us expand this cos a minus b, then we will get ft. So this is your cos. Now cos a minus cos will be your cos a, cos b plus sin a, sin b, and then we will have dt into ds. Now if the function is even, suppose that our function fx is even. Now if this fx is even, then you consider here we have ft and here we have cos st. Now ft is even, cos st is even, so the integration with respect to t will become 2 times. But here you can see that our ft is even but sin st is odd. So the integral minus infinity to infinity ft into sin st will be 0 because of the definite integral. So this second term will be 0 because integral minus infinity to infinity ft sin st will be equal to 0, whereas integral minus infinity to infinity ft cos st will be your 2 times 0 to infinity ft cos st. So if fx is even, then your fx will be 1 pi 0 to infinity. Now this will become your 2 times 0 to infinity. Then in the bracket we will have ft cos st cos sx dt ds. So this is equal to 2 upon pi, then 0 to infinity. Let us denote this bracket ft cos st dt. Let us denote this bracket if f C of, say, if f Fourier transformation of, say this is your cosine transformation of fx, say this is your FCS, and suppose that this is your FCS. Suppose this is your FCS, then we will have fx equal to 2 upon pi 0 to infinity. Now here we will have FCS cos Sx ds. Now here, now in this case, this transformation is known as Fourier cosine transformation. If this is equal to this thing, then this FCS is known as Fourier cosine transform of fx. Then this FCS is known as Fourier cosine transform of fx, and from here this will be your Fourier, then this is, and this will be, and fx equal to 1, fx equal to this one is known as Fourier inverse cosine transform. So this is your formula. So this will be your Fourier cosine transformation. This will be the Fourier cosine transformation of a function fx, and this will be your inverse cosine transformation of a function fx. Okay, here we have 2 upon pi. This 2 upon pi can also be written as square root upon 2 pi into square root upon 2 pi. So if the square root 2 upon pi of the bracket is written here, then we will get root 2 upon pi here and root 2 upon pi here. So this will be your another set of formula. So we can also write some author. Now during my question I will use this formula, but this 2 upon pi can be written as under root 2 upon pi into under root 2 upon pi. Now send one root 2 upon pi here, then we will get root 2 upon pi here, and we will have one more root 2 upon pi. So at this place we will get root 2 upon pi. So some authors use Fourier cosine transform of fx as root 2 upon pi 0 to infinity ft cos st dt, and inverse as fx equal to root 2 upon pi 0 to infinity FCS cos Sx ds. So you can use any formula from these two one. So in the questions I will use this one, and you can also use this formula during your questions. So this was your Fourier cosine transform. Now if the function is odd, then what will happen? Now if fx is odd, then we will have, then the first term will become 0 and we will have the second term, and in the second term the first term was ft cos st minus sx, so that will be your cos st cos sx, and the second term was your sin st into sin sx. So if your fx is odd, then we will have this term, and then this will be your sin st, and here we will get sin sx. So now this will be known as, now if this, suppose that if we assume this one as this term, if we assume this integral as fss, then this fss is known as Fourier sine transform of fx, and its inverse transformation will be this one, and the inverse transformation of fx will be your 2 upon pi 0 to infinity f of the Fourier transformation of sine or you can say Fourier sine transformation into sine Sx dx. So this will be your inverse sine transform of a function fx. Now again we can break this 2 pi in two parts. Some authors use this formula sine st dt, and here sine Sx ds, and here we will have f of s. So we have these two sets of formulae, and you can use any one. So in my problems I will use this formula, and you can also use this formula, and it is easy to learn, because here the coefficients in both cases is root 2 pi, and the coefficient for previous Fourier sine integral was 1.2 pi. So now let us solve some questions. Find the Fourier transform of fx equal to x when your mod x was less than or equal to a, and this is 0 when your mod x is greater than a. So find the Fourier transform of this fx. Solution. Now we can also write this fx as x. Now what do you mean by this mod x less than or equal to a? If mod x is equal to plus x, then we will have x less than a. Now as we know that mod x has two values, either plus x or minus x. So if mod x is x, then we will have x less than a. Now mod x, another value of mod x is minus x. So in the second case, if you multiply this by minus n, we will get x greater than minus a. So the first equation means x is greater than minus a and less than a, and here 0 for the other cases, for the remaining cases. So mod x less than or equal to a means your x is lying between minus a and plus a. Therefore, now Fourier transform of fx, now use your formula, will be equal to minus infinity to infinity, infinity to infinity, and ft e to the power I st. Here we have I st and then dt. This was the Fourier transformation of fx. Now as you can see that here our x is lying between minus a to a, so this will be from minus a to a, and the value of fx was fx in this case, so we will write ft equal to t and e to the power I st dt. Now the integration of this term will be, now this is equal to t, integration of I e to the power ist will be e to the power ist upon is, then minus, the difference of t will be 1, then here we will have e to the power ist upon I square s square, then the limits from minus a to plus a. So now in the first term we will get at t equal to a, this will be your 1 by a, that means here we will have a e to the power isa, and then in the denominator we will have is. Now if t equal to minus a, then again we will have minus minus plus, this will be your minus isa divided by is. Now here as you can see that our I square is minus 1, so this will be your plus, so here we will get 1 upon s square e to the power isa minus e to the power minus isa. Okay. So now we can combine these two terms. So on combining the first term, we will get, the first term will be, now this can be written as 1 upon this can be written as a upon s e to the power isa plus e to the power minus isa into I, and here we can write 1 upon s square e to the power isa minus e to the power minus isa. As you know, plus e to the power I minus I theta is equal to 2 cos theta, and e to the power I theta minus e to the power minus I theta is equal to 2I sin theta. So now this will be your a upon is. Then we will have, here we have plus sign, so we will get 2 times cos theta, and in place of theta we have as, and here we will get 1 upon s square, then 2 times I into sin theta, that means sin as. So that means we will get 1 upon s square, and this 1 upon I will be your minus I, so we will get minus I here, so this will be your I, and we can also take this 2 common, so this will be your minus a cos as. Then here we will have, we have already taken, and again we will have a s, so this will be your minus as cos as, and here we will get, we have already taken 2I upon s square common, so here we will get sin as. So this is your the Fourier transformation of the function fx. Therefore, Fourier transformation of fx is equal to 2I upon s square. Then in the bracket we will have sin as minus as cos as. So this is the Fourier transformation of this function fx.